Hello everyone, this is Mustafa Milani from the University of Western Ontario, and I will present Preserving Diversity in Anonymized Data. This is a joint work with Yu Huang and Fei Chiang from McMaster University. Okay, so I'll start by the motivation in this work. The paper is about privacy preserving data publishing, which is the problem of publishing data for a downstream data analysis task with two objectives. The first objective is to protect the privacy of the individuals in the published data. And the second objective is to make sure that the published data is useful for data analysis. A common privacy model in data publishing is data anonymization, and in particular k-anonymity. So starting from a relation like this, which is about patients in a hospital, k-anonymity is achieved by suppressing values, which is replacing those values with the stars to prevent re-identification of individuals. And but that's done by placing them in groups of k other individuals with the same quasi-identifiers. So these identifiers are attributes like gender, age, address, or ethnicity that together they can identify a person. So the result of k-anonymity is going to be a relation like this that, so in this case, is 3 anonymous. So the existing anonymization methods, like algorithm for k-anonymization, they ensure that the published data is useful by minimizing information loss, which is often measured by minimizing the number of these stars that are introduced in the published data. And they ignore basically the diversity of values in the initial data. And but this diversity, like diverse values that they might exist in the initial data, they can be useful for these downstream data analysis tasks that they use these published data sets. So to address this issue, in this paper, we formalize and solve the problem of K and sigma anonymization. Here, sigma is a set of constraints that represent diversity in data. So the inputs to this problem are relation R, diversity constraint sigma, and anonymization value K. In our running example, we have this relation about patients, and then we might have diversity constraint, like a constraint like this that says that requires this table to have at least 2 and at most 5 individuals of ethnicity Asian. And this is obviously, this constraint is satisfied by this relation because of the last 3 records. Then the expected output in this problem is a relation R star that is obtained from R by suppressing some values to make it K anonymous. And we also need the relation to satisfy these diversity constraints. And also we like a typical, like usual K anonymization problem, we also need the result to have minimum information loss. So in this example, we might like this particular relation satisfies all these conditions because we have obviously it still satisfies the diversity constraint, and we have minimum information loss, and also the relation is K anonymous. So this problem of K and sigma anonymization is obviously NP hard because it extends K anonymity, which is also NP hard. And in this paper, we present a solution based on a solution to this problem based on clustering. The idea of clustering based on anonymization is to find clusters of records that share some attribute values. And that means if we suppress values in one cluster to form a k-anonymous relation, we can preserve these shared values. So in our running example, if we form a cluster including the last 3 records, then in the final instance, we can preserve the values of Asian and female, and we can preserve the diversity constraint. So the idea of our solution is to form these clusters in a way that we can preserve these constraints. So we call it diverse clustering. And we show that this clustering problem can be reduced to graph coloring, where each constraint is a node and each cluster is a color that we assign to the node to satisfy the constraint. We also apply, so to solve the problem, this graph coloring problem, we use a typical coloring algorithm based on backtracking. And we use two optimizations to improve the performance of our algorithm. So the general overview, this is the general overview of our algorithm. It's called DIVA, which stands for Diverse Anonymization Algorithm. So in DIVA, the first phase is diverse clustering that I explained, and then is suppression to suppress values in the clusters, in the partial clusters to satisfy the constraints. And for the rest of the tuples that are not included in the clusters, we use existing anonymization techniques to anonymize those tuples, those records. And at the end, we integrate the records that are obtained from the anonymization algorithm, like external anonymization algorithm, and our diverse clustering technique to generate the final instance. Now, to evaluate our solution, we use 3 real data sets and a synthetic data set for testing runtime. Our experiments, they evaluate the runtime and accuracy of our solution, where accuracy is measured in terms of how close our solution is to the optimal solution to K and sigma anonymization problem. And the results, they show that our algorithm, especially those versions of the algorithm with optimizations, they scale by increasing, scale well as we increase the number of constraints and the size of data. And we also show that our algorithm, like different versions of our algorithm, are more accurate than the existing K anonymization techniques. And to conclude, we defined the problem of K and sigma anonymization problem, and we introduced an effective, like a solution algorithm to solve the problem. For our future work, we will extend the privacy models used in this work. And we also plan to implement a distributed version of the DIVA algorithm to improve its runtime.